Hello everyone. This is an introduction to sequence modeling using RNNs and LSTMs. Sequence modeling is a machine learning approach that deals with sequential data, where the order of elements matters. This can mean temperature variations throughout the year, stock price changes, language and sentences. There's a lot of sequential data out there where modeling is applicable. Sequence modeling can mean predicting the next piece of data in a data stream, evaluating a sequence of information, or generating new sequences using autoregressive properties. As a foundation to sequence modeling, RNNs and LSTMs are pretty good at giving an introductory grasp. I'll not only be giving a high-level understanding of both of these types of models, but I'll also delve into some more technical aspects that I think are worth looking into. So, let's get started. Let's go ahead and start with a blank canvas. You should already understand what neurons in a traditional neural network are. If not, I'd recommend reviewing what those are before watching any further. Our neuron, of course, has its weights, dimensionally equivalent to our input vector x, it has its bias, and it probably has some type of activation function. Here, I denoted it as a sigmoid function, but it really could be anything. The output of our single neuron is y. How can we adapt this model to process sequential data? A first instinct thought might be to simply pass in our entire sequence as our vectorized input x. However, upon further thought, such an architecture would not be adaptable to sequences of different lengths, as these neural networks are locked into the dimensionality they are trained on, and cramming information into a lower dimension would destroy information our model might need for inference. Here's an idea. Why don't we just run our sequence of data through the same neuron multiple times? Well, there's some pretty clear issues with this architecture. A pretty clear issue is that our nodes have no sequential bearing. Our model doesn't know anything about the sequence apart from the single data point it's considering, not even where it's located within the sequence. Okay, well, let's try a slightly different layout this time. This time, instead of passing each data point through the same neuron, we'll adapt different neurons, each pertaining to a different time step. This can also be done with the same neuron, just inputting another parameter as our time step. In our current architecture, this would mean that x0 is always processed by neuron A0, x1 by A1, and so on. A few glaring issues should be apparent. Our biggest one is that our different nodes have no information on any other part of the sequence. Ideally, our model should be able to take into context all of the data that occurred before the time step we're on now. So, if our model is processing x2, for example, it needs some way of taking into account x0 and x1 into its inference for y2. Additionally, if we are sticking to the architecture in which we use different neurons for every time step, we've broken our model's adaptability to sequences of different lengths. Let's go back to our idea earlier, where we pass each data point through the same neuron, except this time, we want to retain some information about previous inferences. Thus, we are effectively maintaining some state between each time step of our data. Our neuron will take into account the state at the previous time step and generate a new inference, as well as update the state to pass to the next time step. It may be the case that our new state is different than the output of our neuron at this time step, or it might be a function of our newly calculated state, as denoted here. Note that the calculation of our new state takes into account the old state, ensuring that the transfer of information from all previous time steps to a new time step is possible. Thus, our recurrent neural network, RNN for short, is born. You'll often see RNNs in one of two forms, unraveled on the left and raveled on the right. By nature of processing sequential data, our model will also naturally generate sequential data. However, we might not want sequential data as an output. For example, we might just want the last output of the final time step. We can adjust our training objective and our loss function to tailor the RNN to our needs. Why don't we step through a high-level example using natural language processing? As a quick disclaimer, RNNs generally don't have the complexity to perform well at language tasks. This is a super high-level example just for understanding. Let's say we're trying to train our RNN to predict the next word given a sequence of words. In this example, our phrase being, "the boat was in the." Our model, after encountering the word boat, is able to pass its semantic meaning to later time steps using the model state, from which the model predicts the word water. The boat was in the water. Remember that the only way for the model to have context of previous time steps is the previous time step state. This means that as the number of time steps increases between two data points, the amount of information that can influence later time steps will likely be bottlenecked. Let's go ahead and step through another example. In the same context, let's consider the sentence we want our model to process as, "I moved to China, ... I'm speaking more," where ... is some long string of words that aren't totally relevant to the word we're trying to predict. Because the word that gives our model the most context into what word comes next, China, is so far from the final time step, it is difficult for our model to translate that information through the state for all these time steps. So, we've encountered one potential problem that RNNs give us while processing sequential data: an inability to retain integral information over many time steps. This also creates a large recency bias in the state for the data the RNN just processed. Before we move on, I want to delve into what an RNN state exactly is. Our RNN is trained to preserve context and information it deems is important between time steps. At any given time step, our model projects the previous state and the current input into the hidden space using the weight matrices WH and WX. You might notice that, contrary to traditional neural networks, these weights are in the form of matrices instead of vectors. Because the dimensionality of the input vector and the hidden state are generally different, our weight matrices are shaped accordingly to map the input space to the hidden space. Thus, intuitively, WH, which is the weight matrix corresponding to the previous state, is a square matrix, and WX, the weight matrix corresponding to the input matrix, is shaped hidden by input. Thus, when left multiplied by xt, our input vector, the output is a vector in the hidden space. Let's take a step back and consider how we would train our RNN. If we care about our model's entire output sequence, for example in translation or speech tagging, our loss function should take into account every output of the model. Thus, the model would be evaluated based on its performance at every output time step, y1, y2, y3, etc. And the gradient would flow backwards from each of these outputs, with parameter updates aggregating over all time steps. On the other hand, if we only care about the model's final output, for example in sentiment analysis or next word prediction, then only the last output contributes to the loss function. This means the model is evaluated based solely on its final output, and the gradient flows backwards from just the last time step. In either case, updating gradients requires the model to propagate errors backwards through time, either from each time step or from the final time step, resulting in updates that span many recurrent steps. This brings us to another major issue with RNNs. One of the major challenges in training deep or recurrent neural networks is the vanishing gradient problem. As gradients flow backwards from the output layer during backpropagation, repeated multiplications by values less than 1, through the chain rule, can cause them to shrink exponentially. In RNNs, this issue is even more pronounced because the same weights are applied at every time step, and the gradient must flow backwards through many recurrent steps. As a result, earlier time steps receive much smaller updates, and the network struggles to learn long-range dependencies. I won't delve too deeply into the math here, but as the sequence length increases, the learning efficiency of RNNs drops significantly due to this effect. Alright, let's first recap our discussion on RNNs before we move on. RNNs can get you pretty far in sequential modeling, and they're a pretty good starting point for efficiently modeling sequential patterns. However, with more complex patterns that require long-term memory and dependence, RNNs struggle and have a huge bias towards recent data. Increasing the complexity of our RNN to combat this often just results in vanishing gradients. Still, for simple tasks like predicting the temperature or basic trajectory estimations, RNNs do a pretty efficient job. Let's consider the RNN's architecture once more. I've unraveled the RNN into what you see here, with the input xt, the activation function, in this case tanh, and the output for this time step yt, as well as our connections to the node of the previous and subsequent time steps. In more complex cases, this single connection between time steps isn't comprehensive enough to give the model an accurate context to make decisions. In order to better inform our model, a connection that focuses on more recent data, a sort of short-term memory, and a connection that contains long-term dependencies, a sort of long-term memory, is necessary. How we manipulate our information into these forms is a bit complicated, but our RNN sets a pretty good foundation for learning how these work. Here is the long short-term memory network, also known as the LSTM. At first, pretty daunting, but it can be segmented into a few different components. You may also notice there are now two connections between time steps instead of one from our RNN. If you want to see if you can decipher some of these components into their parts, go ahead and pause this video. Otherwise, let's start breaking this down. Firstly, let's create some standards here. Yellow cells are weighted cells. All of the inputs to these cells have their own weights associated with them. In our architecture here, we see 3 sigmoid functions and 1 tanh function, all with their own weights. Gray cells are operation cells. They simply perform their respective operations. You may notice there is what appears to be a multiply and add operation cells. These cells take in 2 inputs and perform either element-wise multiplication or addition. There is also another tanh operation cell with no weights associated with it. It basically just squeezes our inputs between -1 and 1. More on this later. Lines that flow into each other represent concatenations, and lines that separate are copied into both branches. Into and out of our cell, there are 2 points of information transfer between the time steps: CT, our cell state, and HT, our hidden state. This is what our LSTM uses to infer context of prior time steps. Let's first focus on our cell state. I've removed everything that doesn't directly modify the cell state. Notice that there are 2 connections to the cells. These are memory gates. Memory gates are how our model manipulates the flow of information to and from the cell states. Part of our model's training is for it to learn exactly what information should be let into the cell state here, hence the weighted cells. Let's focus in even more and zoom into exactly what this first gate on the left is. This first gate is known as the forget gate, which takes in our input at this time step, xt, and the hidden state of the previous time step, ht-1. Using a weighted sigmoid function, our LSTM creates a vector, ft, representing what our model wants to element-wise multiply to our cell state. As the name suggests, the goal of the forget gate is for the model to remove information, or basically forget memory, from our cell state that it deems is now irrelevant and unhelpful to its inference. How exactly does our forget gate actually remove information from the cell state, though? I think the best way for us to understand how the LSTM forgets information is through an example. Consider this scenario. Our LSTM is tasked with judging a fruit based on what the input specify. Here, our model takes in a sequence of words, here including the words lemons taste. Let's say that somehow, after encountering our word lemon, our cell state becomes CT is equal to 0.4, 0.9, 0.9. This is a drastic oversimplification, but bear with me that it represents what our LSTM has learned to keep within the cell state. It is impossible to say exactly what these values might mean within the LSTM, as in this vector space, any dimension might represent hyper-complex relationships. But let's again oversimplify and say that these three values correspond to commonality, yellowness, and sourness. Upon encountering the word taste, the forget gate in our LSTM generates ft, which is now equal to 0.1, 0.1, 0.9. Intuitively, this is like our model saying that we shouldn't care about anything other than the dimension relating to taste. In this case, our third dimension being sourness. So, as we move to the time step in which we are considering the word taste, we'll perform element-wise multiplication between the previous cell state and our newly generated ft. Thus, we get our modified cell state CT prime to be 0.04, 0.09, and 0.81. And yes, this is CT prime and not CT. We'll be able to compute CT from CT prime after the next gate. Remember, there were two. From this, we can see that our LSTM leveraged the forget gate to suppress irrelevant information, allowing the model to emphasize more relevant data. Of course, we can't only forget information. There must also be some mechanism through which our model inputs new information to its cell state to draw context from. In order for our cell state to gain new information, our LSTM uses the input gate to add information to the cell state. You may notice that our input gate has two weighted functions, the sigmoid function, producing what we'll call IT, and our tanh function, producing what we'll call CT bar. Thus, the output of the entire input gate, which will be added to our cell state, is IT times CT bar, which will equate to capital IT. Let's step a little deeper into the intuition behind this structure. One question you may have is why our LSTM has two weighted cells instead of just one, and more specifically, why they are a sigmoid and tanh function. The intuition behind two weighted functions is that our model needs to learn how to control how much new information to write and what that new information is. Our tanh function not only quashes values between -1 and 1, but it can better actively shape that information itself, like change its sign. Our sigmoid function allows the model to selectively control how much of that information passes through, kind of like a valve or a filter on top of the tanh output. If we only had the tanh function, we would only be able to shape our input, but it would be very difficult to effectively gate it. If we only had our sigmoid function, we would only be able to decide what of our input passes through, but not as easily shape it or change its sign at all. The sigmoid function controls how much gets in, and the tanh function decides what gets in, and it gives the model a lot more flexibility to work with. This is the second and last gate that actually manipulates information into the cell state for this time step. We can calculate CT from these two gates. From the formula, we see that CT equals CT prime from our forget gate plus capital IT, which is the output of our input gate. We've updated our cell state to pass to the next time step, but we still need to update our hidden state and generate our output. Thus, our output gate takes in information from the previous hidden state, the current input, and the updated cell state to generate an output. I won't delve too deeply into this, but essentially, our model takes a tanh of the cell state, which, in a sense, normalizes our cell state in preparation for the next operation. Our model also takes a weighted sigmoid function, essentially gating the information from this current state and the previous hidden state. Intuitively, our hidden state represents our short-term memory, more easily influenced by current inputs xt. Thus, our output gate uses a sigmoid function to selectively gate our short-term memory in the context of our cell state, intuitively our long-term memory. You may also notice that in this architecture, our output at this time step is the same as our newly generated hidden state, though a similar workaround can be made as was done in our RNN architecture to change that. Again, our hidden state represents our model's short-term memory, and our cell state represents our long-term memory. This allows our model to form long-term dependencies, creating inferences with the ability to take into context information sequenced many time steps prior. This also dampens the bias towards more recent data. This fixes one of our integral problems with RNNs in the first place. But, of course, we had one other major issue as well. How does our LSTM architecture solve our vanishing gradient issue? To recap quickly, our RNN's gradients vanish because many time steps and nodes means long sequences of multiplications that our gradient must be chain ruled through. Once these values drop below 1, multiplying them together just makes them all smaller and smaller. Because changes to our cell state in the LSTM are often additive, the chain rule doesn't apply, and instead derivatives are simply added together, meaning small gradients generally won't compound on themselves and force everything to be tiny. A good way of thinking about this intuitively is if earlier time steps have the ability to have an impact on a cell state many time steps in the future, then there must be some substantial path for the gradient to flow backwards on. So far, perhaps I've made it seem as though LSTMs are superior to RNNs in every way, but this is certainly not the case. LSTMs have a lot more complexity than RNNs, and while that affords them the ability to identify more complex patterns and develop more long-term dependencies, this also makes them more complicated to implement, take longer to train, and are often overkill for the task at hand. At the same time, if there is some complex issue to be solved with LSTMs, it is likely that even a massive complex RNN model would struggle learning after a certain point due to vanishing gradients. As a good rule of thumb, you can always just apply Occam's razor and start with the RNN before moving to a more complex model if needed. That pretty much wraps up our discussion on RNNs and LSTMs. I hope this gave you a solid foundation in sequence modeling, one that you can hopefully build on in the future. If you're interested in diving deeper, here are a few directions I think are worth exploring. First, gated recurrent units, or GRUs, are a popular alternative to both RNNs and LSTMs. They solve the same issues we discussed with RNNs, but are simpler and more efficient to train than LSTMs. If you followed the logic behind LSTMs, GRUs should feel pretty intuitive. Second, digging deeper into how gradient descent works with these specific models can really strengthen your understanding, especially how LSTMs help mitigate the vanishing gradient problem. I tried to give an intuitive overview, but seeing the actual math and numbers can really make it click. Finally, I highly recommend looking into the transformer architecture. In short, attention is all you need. Unlike the models we discussed, transformers don't really rely on recurrence or memory. Instead, they use attention mechanisms to relate all tokens to each other simultaneously. It's a very different approach to sequence modeling, but it's what powers nearly all modern large language models today. This is the first time I'm making one of these lecture-style videos, so I don't really expect many people to see this, but If you do have feedback, if you do have comments, criticisms, questions, feel free to leave a comment, and I'll try to get back to everyone I can. But thank you for watching.